Oh yeah. So a little typo on the homework sheet, just in case.
At least all the ones that have questions on it. Yeah.
All right, guys. Anything else from homework? And a little typo on the homework sheet. 20 through 55 is supposed to be every fifth one, not all of them. Yeah. Okay. Any questions from homework? I had a few good ones in office hours. You guys are good? Yes. And you guys are all aware, I did update the thing on Canvas. I have no idea if I actually said this in class, but you're all aware that we have on-campus tutoring now, right? Did I tell you that? There's people, there's an actual person to go see in the Mass Study Center. Okay. Sometimes that person will be me. I'm in there every now and again. All right. So if there's no questions from homework, there's one thing I want to finish up from section 3.1. We did do part of 3.2, the product rule. And then we got to do quotient rule. And then we'll see what else is left. The one thing, all right, so I need you guys to help me out before we do this next thing here. All right, let's see if I can get you guys to help. Get your calculators out. All right, just to save some time, can this side of the room, you guys, do this one? Make a table, right? Make a table of values. Try to figure out what this is. And you guys see that this is indeterminate, right? Okay. And then the other side of the room, you guys do with the 3 there. There's a purpose to this. Okay, I'm gonna wake this guy up and we'll do some funkier shit here in a minute. Some really cool shit, just in case you still have some trouble with this kind of thing. No, Jeff. Dadgummit. Right? That's how you make a table of values, to sort of investigate this thing. Yes?
What are we solving for?
We're just figuring out these limits. Yeah, that's all. We currently, you guys, this could be just me. I just want to do a review of limits, but you know there's something else happening. If you just came in, there is a typo in the homework. You don't have to do all 20 through 55 in 3.1. It's supposed to say every fifth one after that. So if you did them all, extra practice. You're gonna kick ass on those derivatives. And you're like, yeah, Jeff, whatever.
Right.
All right. So can you guys help me out? What do you guys get for this little table? What do you get for 0.1? Anybody did that yet?
Oh, sorry, not 2. 1, 2, 3.
Oh, I'm sorry. Yeah, I'm sorry. So it's, yeah, the 2 stuff. So this side, right?
Yeah.
What'd you get for the first one? Sorry.
0.7177.
7177. I like it. Somebody else tell me 0.01. You guys see that? Yeah.
695.
6956 roughly.
Yeah.
And then somebody else, the last positive one, 0.001.
0.693.
6934. roughly? Okay. And for the negative stuff, shit and a half. All right, there we go. Aw. What do you guys get for that while I try to...
26.9.
Oh, I see. Yeah, 6929. 6908. 6697. So if you look at it this way, it looks like it's going to roughly 693 something, right? Kind of split the difference and see what it is, but it's roughly 693 something. All right, now what about you guys? Let's check in with you guys. I should have left more room here. Sorry, say it again. 123. I like it. Look at that. And then what about somebody else? 0.01. Did you guys get that? 1.047. 1047. Okay.
Yeah.
0.001.
1.099.
1.099. And then if we go at it from the other side, who's got the negative 0.001? 1.098. 926. 0404. So if you look at it from the left, from the right, it looks like I would have to assume this is going to 1.10 almost, right? Or 1.09 something, we'll say. All right, now. So when I have a 2 in there, they're basically the same kind of function, correct? I just have a different base here and here. Can you real quick tell me what is the natural log of 2?
About 0.693.
Somebody knows where I'm going with this, maybe. 0.693. Isn't that what we got for the limit? What about, what's the natural log of 3? 1.09 stuff? Isn't that what we got for that limit? So it seems as if, can somebody please tell me, and we're actually going to sort of prove this later, but for right now, we're going to use this. If I just put B in there, what is that approach? What can we say now? ln of B. Okay, I like it. Let me stop for a minute. There's no reason in hell that you would actually think to do that by yourself. This is sort of building on something we're going to do later. Right? So what's really weird about math, just a real quick side note, there's very little math that we actually teach in the order it was discovered. We actually did a lot of math 280 stuff and then figured out 180 stuff from it historically. But then we said, oh, when we teach this shit, we better teach it this way so it makes some frickin' sense. Okay, I don't know if you guys, it's just a little side note. Okay, what does this have to do with anything? This is interesting by itself, maybe, yes? Isn't that kind of interesting a little bit? All right, now it's going to get even more interesting, is my hope. So what if I have this? Can you guys set up for me the limit definition to figure out f prime for b to the x? And I still have it up here too, right? This is the good old limit definition, yes? I told you it was never going to quite go away, but we're not going to do it nearly as much. I'm going to catch up to you guys. That's right, I was going to do that. Oh, that's too bad. So this will be, now let's see, what did you guys get it for the top? Good. Throw an x plus h in there. Of course, minus the function itself divided by h. Now that looks like you could do nothing to it, yes? Does anyone think, like, you look at that and you're like, what the hell am I going to do with that? There's one thing you could do that's going to lead to another big thing. What can I do with this? Do you guys see? You can do something with that. When do you add powers? Isn't that what's happening? When do you add powers? When I'm multiplying the same base. So what must this have come from? B to the x plus h must have come from b to the x times b to the h. Kick ass. And of course, now what can I do on the top?
Factor.
And we know what this is, don't we? What is the limit as h goes to 0 of b to the x?
1.
Does b to the x give a shit what h is doing? Does h have any control in b to the x? So b to the x is a number for whatever b and whatever x, yes? So the limit of that is b to the x. As h goes to 0, b to the x is just like, I don't care what you're doing. Really, is that cool? Yes? So this is b to the x. And of course, we just figured out what this is. What's the limit of that? ln of b. So now we know, Jeff, now we know, given any exponential function, this is its derivative. So for example, okay, is everybody with me? So that is another derivative formula that you can write down and memorize. You're going to memorize all of the derivative formulas. Yay! Okay, so a real quick concrete example. If I had 7 to the x, what is f prime of x? Yeah, it's 7 to the x times natural log of 7. That's the definition. That's how their derivatives work. Can somebody, what would be the best base considering the definition of this guy's derivative? What would be a kick-ass base? 7 sucks. Natural log of 7, do you like that number?
1.
It's never done it. 1, why would 1 not really be great?
0.
Well, because 1 to the x is 1. Yeah. What base works really well with natural log? In fact, it's the definition of natural log is based on this base.
10.
Not 10, that's log, that's the common log. E.
Oh, okay.
So what if I have f of x equals e to the x? Yeah, it's e to the x, natural log of e. Natural log of e is 1. Okay, that's incredible. If you think about it for just a minute, we have discovered a function whose derivative is itself. It is its own derivative. So can somebody very quickly tell me, if I keep going, pretend that the line's not there, what is f double prime of x? Here's how we write this. What is the 807th derivative of f? Of course, frickin' e to the x. It's eternally e to the x. That kicks so much ass. The only other function we know right now that is its own derivative is 0, which is really boring. It's the derivative of 0 is 0. It's the derivative of this. It's boring. This is interesting. And if you look at it, what does it look like if I graph this thing? Can somebody do it in the air for me?
It looks like, from your perspective,
You're thinking ln. You're thinking natural log. What is what is a to a power? Yeah, looks like this, right? Or from your perspective, I think is that your perspective? I don't know. So it's going to look like this. Yes. What's the slope back here?
0.
Close to 0, but it's positive. Yes. It's always positive, but it's really small back here. So if I start to draw the derivative, isn't it growing? Isn't the slope growing as I move along? So that kind of makes sense, but it can't be just any base. I always think about this. This piece here is the adjustment to make the slope work if the base isn't E. E is the only base where it lies right on top of itself. Any other base, it needs a little adjustment. And that's the ln piece. It's its little adjustments to make it fit perfectly. All right, let me stop for a minute. I got a stupid little comic I put on my Math 280 syllabus, a wild e to the x has appeared. You use, it's like the Pokemon thing. You use derivative. It is not effective, because it stays the same. Anyway, yet another dumb joke in a long line of dumb jokes. All right, so now watch this. What was the product rule again? If I have a function that is the product of two functions, this idea is going to carry through a lot of different things. They both get a turn. They both get a turn at having their derivative taken. So what is the rule then? You guys remember? F prime. So F gets a turn. Plus. And then G gets a turn. And we actually proved that last time. So, if I had a function that was this, take that guy's derivative. And if you need to, you could identify which is F and which is G, right? But let me try to show you how to not do that. So what I'm about to tell you, hopefully some of you guys did it this way. What I'm about to tell you is huge. You write what the rule says to do, and then you do derivatives. The people that make mistakes are the people that try to do it all in one step. And you're going to forget something. So the rule says this guy gets the derivative plus the other guy's term. That's the rule, right? That is exactly what the rule says. Then I do my derivatives. I don't worry about derivatives at first. I just write the rule. And now, of course, what's the derivative of this bad boy? 6x squared. So this is now the same. And, of course, this guy's derivative is? Holy shit. All right. So that is h. You didn't put a prime there, Jeff. Come on, dude. So really soon, it's almost good that I made that mistake. You really got to be careful about when you actually start to take a derivative. So this is my derivative line, right? Because sometimes we're going to want to simplify the function first. So if I was just simplifying, I wouldn't put h prime, but people do that, and then they think they're done. Look at that, I did h prime. No, you didn't. You just rewrote what h was, and then you've got to do a derivative. Okay, maybe.
Would you want us to simplify it, like pull like even the x out, and then do?
Oh, it depends. So it's the funny thing is the amount that you want to simplify or rewrite the answer depends on what you're supposed to do next. The whole point of this problem right now is just to find the derivative. If I then said find all, okay, let's do this. If this is part A, and part B says find all locations where h of x has a horizontal tangent line. Right? What does that mean? When will it have a horizontal tangent line? Yeah, when the slope is 0. I love it. And that could be a location of a maximum. It could be the location of a minimum. Minimum? Sure. Or it could just be a place where the function was like, I'm going to turn, no, I'm not, haha. So very soon we're going to start to determine ways to tell which one of those it is. But right now I just want to know where the tangent line is horizontal. So then you've got to solve this. So then you want to do what? Factor. What comes out?
E to the x.
Definitely e to the x. And? 2, x squared, right? So what's left? I got a 3 left here, yes? Plus an x. So where is this thing horizontal? X equal to what? Oops, I almost put it. X equal to what? Are there 3 places? Are there 2? When is this 0? When x is 0? Negative 3?
There's no value to that.
Good. I love it. True question. There's a asymptote at 0 for e to the x, right? It's never 0. So you only get 2 answers. You get 0 and you get negative 3. That's the 2 places where this guy's graph would temporarily flatten out. Okay. Maybe. All right. So that actually is a decent example of product rule helping us with something we can never do ourselves a different way. And real quick, I really want to make this, look here. Okay. What is this guy's derivative? I can't remember if I did this. I don't think I did. Not this piece, but the next piece. What is this guy's derivative? I love it. You guys are like, no tricks here. That's just directly that. I love it. What if I wrote it like this? Is it the same function? Yes. I'm sorry. Go ahead. Kayla?
Where did the 7 come from?
Oh, okay. So a while back, let me see if I have some room for this. Yeah. We went through not a rigorous proof, but a decently rigorous proof that for anything that looks like this, the derivative looks like this.
Yes, I got that.
Good. All right. So here, the 8 comes down, and that power goes down by 1. That's what the rule says.
Oh,
Yeah. Okay. Now, you all agree with me that's the same function, right? In fact, whoever, you would look at the person who did this and didn't put them together, you would look at them a little like, what's your deal? But let's say there is a person like that, and they do this derivative, but what do they have to use then if they keep it written like this? They have to use product rule, right? So what do we get here? Let's see. I would take the derivative of the first dude, leave him alone, plus leave the first dude alone, derivative of the other guy. So the idea of they both get a term is huge. It's going to come up a few times. Let's see if we get the right answer. I think I did something like this. I can't remember. So, of course, this guy's derivative is 5x to the 4th, right? And then this guy's derivative is 3x squared. So sure enough, I get 5x to the 7th plus 3x to the 7th is still 8x to the 7th. Yay! Right? So we expected that, but at the same time, it's good when we learn a new rule, it better work for old stuff. If it doesn't work for old stuff, then it's shit. I have to throw it out. Math has to be self-consistent. Okay, now, I will sometimes get people that forget that product rule says they each get their own turn. So I'll have somebody that thinks the product rule says this. But if you, right, is everybody with me? You guys understand the mistake somebody would make here? They're like, oh, that's easy, that's easy, yay, and I get 15x to the 6th, which is nowhere near what it's supposed to be, right? Okay, good. Bad. Please put in your notes. No. Wrong. Bad. Okay, I like it. Don't leave that alone and say, well, Jeff said this is good. All right. So that's this. Now, let's do quotient rule.
This 3.2?
Yeah, this is still 3-2. So product and quotient rule are both in 3-2. Okay. So of course, this would be a function that is actually the ratio of two functions, right? So You'll all be very excited to know that we're about to bring back the limit definition to course. Can you guys please set up? And I will put it over here for you. Please set up what the limit definition looks like for this. Oh, let's do something. I'm sorry. Are you guys? Let's do this. Again, there's little h's in here, true? Can you guys just make this k of x? So there's not a bunch of h's running around, right? Okay, so go ahead and set up what that looks like. This would be k prime. So there's not work to do here. This is the actual function we're dealing with, so we're just going to plug that. So this will be limit h goes to 0, f of x plus h over g of x plus h minus f of x over g of x all over h, yes? Because that's what the function k is. So when I plug an x plus h in, that's what I get. Now, let's see if we've done enough limit stuff. What's the algebra I would use to try to keep going? What algebra would I do? Yes? Oh, okay. Get these together, right? Get those together. I want to combine those fractions. We've seen enough of these back in chapter 2. Limit of things that were separated, get them together and hope to God something cancels, yes? So let's do it. When I say let's, I mean you. Do it. Do it. Get those things together, and then I'll catch up. I'm going to kind of sort of skip a couple steps just to get to the point, but basically you said it perfectly. This first guy needs what the second guy's got. The second guy needs what the first guy's got. And then they both got this. Is everybody cool with me doing this? Have you guys done enough of this to know that's how it works? It's divided by h, and now it's also divided by the g's. So it's divided by all that shit, h, g, g. Let me know if you're not cool with that. I did skip a couple steps.
Can you do it?
Sure. Okay. Let me see. Do I have a different color? Will it show up? Let's try red. All right. So I had to give this guy a g of x, right? And I have to give this guy a g, Jeff. X plus h. Now they both have this, yes?
Yeah, okay.
Now, let me see if I can sneak this in also. Dividing by h is the same thing as multiplying by 1 over h, yes? And so there you go. H is to get down there with these things.
Okay.
So I could put that together with that, and what's on the bottom? H, g of x, blah, 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 blah. Yeah.
Got it.
Okay, okay. All right, now let me see if anybody, the next thing we need to do, I tried to use it at the wrong time and really messed myself up, but let's see if you guys, what's the weird ass thing that you would probably never think to do on your own that we're gonna try to do here? Anybody know? Do you? Yeah, insert a version of 0 that will be helpful, right? I can add 0 to anything in the universe, yes? So something really weird is when I was taking math courses, I'm talking like math 500 something, I had a list that kept growing of all these things that were equivalent to 1. because I can multiply anything I want to in the universe by 1, right? So it's really weird to think, okay, this is equivalent to 1, this is equivalent to 1, and then I can multiply by that shit wherever, and it might help me with the math I had to do. So this is sort of analogous to this. I don't need a list. What's 0? Something plus the opposite of that thing is 0, right? So I can just use that wherever it's good. And let me think. I don't want to say this. Well, let's see. What am I going to add and subtract? Let me kind of write this. Let's leave some space. Let me put this back here. So let me ask you this. What is this guy missing to become like a full f prime? F of x plus h, I better have a minus f of x, correct? Okay. And what is, and this guy's missing an f of x plus h. Okay, now stay with me. So if I do this, that's sort of the thought process to even consider doing this. If I do this, subtract this. Wait, is that what I want to do? Oh, what did I write down? Oh, I see what I did. Oh, Jeff. Okay. I'm thinking ahead. I didn't write that down, right? Okay. So I put this here. And then I meant to put this here just so I can focus on the middle, and I left my plus h out. And that really freaked me out there for a second. All right, so all I did was I put that there. I put that there, almost did, and now I got it right. And then I could focus on what to add and subtract in the middle. Now, what the hell did that do for us? Well, let's see. What can come out of the top of these two? So let me write it like this. I'm going to write this in a very strange way. All right. Make sure everybody's cool with what I've done so far. All right, so I took a g of x out, and I put this part over that h. Because now what is this piece? If I do the limit of this, what is that the definition of? The limit as h go to 0 of this is f prime, right? Okay. So this is how we kind of try to do higher level derivatives of weird shit, is we try to write down what it is for the weird shit, and then we try to pull out stuff that looks familiar. So what's going to happen over here? Well, what can come out of both of these? And in fact, thinking ahead, what has to be first in order for this to be related to g prime? G of x plus h. So let's take out a negative f of x. And also, let me just say this. This is a derivation of a rule. I'm not going to make you do this by yourself. This is not an example of a problem you've got to do yourself. Are you with me? This is the derivation of a rule, right? All right, so I'm going to take a negative f of x out, and I'm left with that becomes positive, that becomes negative over h. And of course, now I can do this limit. This is f prime. There's g. There's f. This, of course, was going to be g prime. And what happens on the bottom when h goes to 0? Be careful. You get g squared of x. Is that cool? Or you can make it g of x squared if you really want to, right? Okay. Let me see if this will make some sense. So let me write this down more succinctly. This is our quotient rule. And then I want to point out a way to remember this. Do you guys see how it looks like product rule except for two things, right? Doesn't the top look like product rule except for the minus, correct? And then you got these extra 2 G's down here, right? Okay. Which function from the original was on the bottom? G. Let me see if I can kind of tell you this before we get there. Couldn't I rewrite that as g to the negative 1 if I brought it up, right? Wouldn't that be g of x to the negative 1? Because it wants to be on the bottom, correct? So when I take its derivative, wouldn't a negative 1 come down, making that part negative? I really want that to make sense. I'm trying to give you a way to remember why the minus is where it is, right? So that is the guy that's on the bottom. If I had an x down here, couldn't I bring it up and make it x to the negative 1? If I had an x on the bottom, couldn't I bring it up? All right. If I had, ignore the Math 90 graphing stuff, okay. If I had this, couldn't I rewrite it like this? And then what's its derivative? Negative x to the shit, right? So I really want, why is the part where I took the g's derivative, why is that part negative? Because g was the one on the frickin' bottom. It's the one that would have a negative power. So this is effectively product rule, except that is going to make this part negative. So if that was a plus, that top would be product rule, right? Maybe. I don't know. All right, let's do a concrete example. I love you guys. Once we get to chain rule, I can go back and make a lot of other things make a little more sense. Yes. Sorry. Were you not finished?
Yeah. It's like 2 seconds.
No worries. So now we know product rule, we know chain rule, we know exponentials, right? You might, if I'm you, I might just keep a running log of all the stuff because you're going to have to memorize it. I think your book, doesn't the book also have, you guys automatically look in the front and back of your books? No? Whenever you get a math book, dear God, look in the front and back of it to see what there is, right? So let me just point this out. Oh, look at all this shit. All right, so if you look in the back of your book, reference pages, geometry, distance formulas, trigonometry, law signs, beautiful shit, special functions, x's and exponentials and logarithms and hyperbolic, even hyperbolic. Anybody ever heard of hyperbolic functions? Yes? Okay. And then Dugeler. Differentiation rules, right? So you're going to see stuff we have obviously not talked about. We did do this. I sort of made it through that proof. I almost did. And then you got some really funky shit. But anyway, this is a nice quick reference stuff. But you're going to have to memorize most of those. I will have a few that you don't have to memorize. And they're the ones that I don't memorize myself. So, okay. Let's do a concrete example of this quotient rule. So if I had this, you could do it, Jeff. Okay. And I want to figure out the derivative. So, do you know in math how there's songs sometimes to remember stuff? You know what I'm talking about? Like there's a really stupid song for the quadratic formula or whatever, right? And there's mnemonic devices, like the SOAP thing for cubes and stuff. All right, I generally hate that shit because it takes you away from the idea. You remember the thing, you don't remember why it works, which makes your foundation shaky, and when you try to build more math on top of it, it falls over. Now, here's my song for this. I do have a song for this. My song for the quotient rule is top first. Right, that's it. Top first. Whenever you have a quotient, you take the derivative of the top first. So it's going to be top derivative, leave the bottom alone, minus, leave the top alone, take the derivative of the bottom, divided by what?
The bottom square.
Bottom squared. Kick ass. Top first. All right. I mean, this, I don't know. Do you guys know about the whole high-D low, low-D high? Has anyone ever heard of that? I'm kind of making fun of that dumbass song. I'm really sorry because it rhymes two different ways. So I never saw that as useful. But if it helps you out, if you already know it and it's great, fantastic. I prefer my song because it's very quickly over. Especially if I'm singing it, you want it done quick. So what's this guy's, now I can just start doing the derivatives. This is why I like to get you guys to write the rule, because now you can focus on the one little thing you got to do right then. What is the derivative of x squared minus 2? 2x. Is everybody cool with that? We're still kind of new to derivatives, I understand that. But whenever you see power stuff, x squared, you're like, thank God. And the minus 2 is a constant, it goes away. And then times x plus 5. Minus, leave this guy alone. What's this guy's slope? What's that guy's derivative?
1.
Kick ass. Thank you very much. Peace. Now, I showed you on the first day. You don't have to write this down. Just remember. Remember when I showed you this and I said one quick way to make me cry is to say that that's true? Remember that? So if you write that down, gigantic, just freaking shit. It's bullshit. All right. Another way to make me cry is, and again, some of you guys want me to cry, I understand. Another way to make me cry is to cancel one of those. Somebody out there right now did that, or thought they were going to do it. Why is that no good? Why can't I? There it is, Jeff. What's wrong? Can't I cancel one of these? Why can't I?
We don't know if x is negative 5.
No, it's not that. X is assumed to not be negative 5 from the beginning. Yeah, right? What's being divided by x plus 5 squared? Not just this dude is also. So if I kill one of those, he got away from being divided twice. No, we can't let that happen. It's not fair. Okay, so what do I do instead? Distribute that. Distribute that. And then I get x squared plus 10x plus 2. Does that look like it's going to factor? Can you tell pretty quickly that that will not factor? Yes? I like it. And what's really nice about this, I want to make sure you understand, the minute I write a function like that down, let me bring that back up, sorry. The minute I write that down, it's known that x is not negative 5. It just can't be. So what makes beautiful sense here? Where is this thing not differentiable? At negative 5, because the original function was not even continuous there. So wherever the original function is discontinuous, the derivative won't exist there. And wherever the derivative is discontinuous, remember the absolute value where the slopes were different on both sides? That is also a place where it's not differentiable. Okay. All right, all right. All right, here. Oh, shit. Do I have any more blank paper? Yes. Did you ever get that? I'm sorry. You guys all got that? So, let's try a whole problem out. What do we have? We'll get plenty of time. Look at that. It's the worst thing for you guys to hear from math teachers say, right? We got plenty of time. So if g of x, what do you want to do, Jeff? Yeah, let's do something evil. If g of x is 2e to the x over, not too evil, Jeff. Okay, Jeff. X plus 1. Find the equation of the tangent line at x equal to 0. Have you guys ever seen the word equation written like this? So I'm going to do that sometimes. EQ with an N up is like equation. Does that make any sense? No. I don't. It's just the way we do it. So it looks like EQ to the nth power, but do it. in case you're not sure what to do, what's the first step you got to do? Take the derivative, because the first step of finding an equation of any line is to find the slope of that line, which of course is the derivative. I love it. All right, let's see. Can somebody sing the song for me? Oh, thank you. All right. I appreciate you also doing it a little wobbly. Top first. All right. Sorry. So the top derivative first times the bottom minus, leave the top alone, and the bottom gets its turn. I really slammed all this shit in here, didn't I? Chima! Divided by x plus 1 squared, the square at the bottom. I like it. So the derivative of this is nice. What's the derivative of that bad boy? I left with the bad boy, Jeff. 2e to the x minus 2e to the x, and the derivative of this dude, 1, kicks ass, over x plus 1 squared. That is g prime. And of course, I could, if you really wanted to, couldn't I just take 2e to the x out? Something very interesting happens here. What happens when you take 2e to the x out? Yeah, it kicks so much ass. So then I get g prime of x is 2e to the x times x. Just slam an x in there. I don't know if you guys are cool with that. Let me write it better. 2x e to the x over x plus 1 squared. Now I really didn't have to simplify it, because what's the only thing I need to know this for? At 0. I just want to know the slope at 0. So I could have just played 0 in there, but let's, so what's the slope at 0? 0. Doesn't matter all this other stuff, Jeff. It's 0. Should be a 0 there. There you go. So that's beautiful. Let's see if you guys get this, though. What's the point that I know? At x equals 0, what's the output? 2. Right, when you put a 0 in? So here's our first example of when you're going to plug a value in. Know which function you need at that moment. If I want to know the slope, I'm going to put it into the g prime. If I want to know the point, I'm going to put it into g. Okay. So I know the slope is 0. I know the point is 0, 2. Does anyone know what that equation of that line is? Be more explicit.
Y minus 2 equals 0.
Oh, okay. So y is 2. Right? Flat line is a y equals line, yes? So y equals 2. Done. It's flat there. Are you good? Okay. All right. All right. So, next thing. Did I? All right, wait a minute. Hopefully everybody got this here, right? And I'm pretty sure, yeah, we did this last time, this piece here. And then there's the correct derivation of the derivative. All right, so just to remind you guys, I love everybody's getting it out, but we're not going to do anything with that. So I just want to remember that if f of x is sine x, let me do this. Let me bring this back. I need to start writing this more often. All right, is anybody tripped out at what I just wrote?
Yes.
I understand. So, f prime of x is also known as d by dx of f. And the reason that is, what is f prime again? It's the slope of the function. What is slope? The change in the y's over the change in the x's. So this is really the triangle y, triangle x from algebra, but that was big steps. Calculus says I want it to be infinitesimal steps. So that's why we put a d there instead of a delta to represent the small steps. So whenever I see this symbol, I think big step. And what would a big step be? 0.00007. That is a huge step. Holy shit. Compared to what it could be, that is gigantic. This means the smallest possible step you could take. That's what that means. So remember that problem where you had to zoom into the function and you saw that it got straighter and straighter? That's something called local linearity. Locally, it's sort of like the reason we have, well, all right. Do you guys know that there are still people that think the earth is flat?
Yes.
Okay. Holy shit, right? Yeah, that fact by itself tells you we've got some work to do. But why did they think that way? Because we're really close to a curved object where the curve is kind of very gradual. Yes. So we are zoomed in to something that has a very slight curvature. So to us, locally, it's flat. Just like that problem I had to zoom in. Yes? You with me? Okay.
No.
So, sorry?
Not with you.
Okay. Let me see if I can do this real quick. I did this. Yeah, didn't I do this before? Let me do this again because this is good to remember. I got all this stuff up here. All right. Desmos. There we go. All right, that's the snake Desmos. It's like snake jazz. Desmos. Time travel. All right. I can't remember. I wish I could remember the function. I had some funky function here. All right, this is good enough. Do you see how it looks pretty pointed right there? Oh shit, you guys don't see anything. I love you guys. I love you guys. You're all just sitting there like, he's gonna forget, isn't he? All right. Okay. From this level, doesn't it look kind of pointy down there? Would you agree with me? It looks kind of pointy. But we know it isn't, because this is a beautiful polynomial. It's going to be curvy. So the more I zoom in to that point, let's just zoom in. It's already looking less pointy, right? The more I zoom in, it still doesn't look, does it look flat? No. All right, let's zoom in, zoom in, zoom in, zoom in. Is it looking flatter now? All right, what do you guys think about now?
Yeah.
Doesn't that look like a straight line? This is us on the earth.
Yeah.
You're like, I look at my experiences and I know it's flat and you're all a bunch of dipshits.
No, dude, no. You're the dipshit. All right, sorry. If any flat earthers in here, don't tell me. I don't want to know. Okay. Gotta know the truth, man. Shut up. So anything that is differentiable, this will be true. That's what this captures. Oh my goodness. Is that the right one? It doesn't like when it's on the computer. That's what this captures. This is a local flat line. It's got a slope. The change in y over the change in x. This is stupid small to capture the crazy zoom that we do to make it look flat. Smallest step over, smallest step up or down, whatever. That is the slope. That is another symbol for f prime. Why does this thing exist? Because not too long from now, we might want to differentiate something with respect to, instead of with respect to x, I might want to do it with respect to theta, or with respect to a, or with respect to w. So that symbol, instead of just a prime, d by d something tells me which letter is the true variable. Maybe? That's a little bit better notation if you have multiple variables in a problem. You want to know which variable is the one I'm looking at right now. So if there was a y down here, then I would, oh, y is what I'm looking at. That's what I want to differentiate respect to. That's in our future. Okay. So let me write this a better way. If I know f of x is sine x, f prime is cosine x. We proved that before. That's on that paper. In fact, if I look at sine, let's graph f. Right, so sine is the one that does this bad boy here. Enough with the bad boy. I'm never going to stop. It's never going to stop. If you graph this guy's slope, like you had to do back in section 2.8, what's the slope here? 0. What's the slope here? 0. What's the slope through here? Positive, and then it kind of flat, and then it gets its most positive here, and that's where it starts to, right? Isn't that looking like? And then a 0 again there. Isn't that cosine?
Yes.
Basically, that would not be a proof. What we did was a proof, but this is damn good evidence right there. Okay. Now, but the problem is, what if I have cosine? Why? Let's see why that makes sense. We could do a whole limit definition thing, like we did for sine. I don't want to. Cosine, of course, is the octopus. Right? So his derivative, it is 0 here like sine is, but what is between here and the other 0? What's true here? The slope is negative. Shit. And then, of course, it's 0 over here, and it's positive between there. That does look like negative sine. Looks like sine that's been flipped. So sure enough, if you did the limit definition, you would get negative sine. Really quickly, this is the next place. Remember something about cosine? What was cosine's personality?
An asshole.
He's an asshole. Do you see how this captured the idea too? Sine is like, okay, cosine there, you're my derivative. Cosine, negative sine. Screw you. No? Maybe? No? I don't. This is not the way that math was considered when they first created it. They weren't saying, yeah, let's make cosine an asshole. It's just what happened. Okay. Now, how would you figure out? We know this. This you can now add to your known things. That is a known thing. This is a known thing for us now. Can you please tell me what the derivative of tangent is? I'll wait. We got a very good first step. Isn't tangent sine over cosine? Which tells you you could use what rule to investigate it? Good, do it. I'll wait. I'll be right here. I'm gonna go to there, maybe. So of course we have our beautiful song, right? Top person. So derivative of the top, and the bottom just sits there. Now the top just sits there, and the derivative of the bottom gets a term. And of course divided by, we'll write that better in a minute. What's the derivative of sine? Cosine. So I get cosine squared x there, right? Is that cool? And what's the derivative of sine? I'm sorry, derivative of cosine? Negative sine. So wouldn't that become plus then, right? And if somebody out there doesn't know what the top is, I'm going to go a little bit crazy. What is cosine squared plus sine squared? 1. And what is 1 over cosine? I know it's squared. Who cares? 1 over cosine, so the answer will be that thing squared. What is 1 over cosine defined to be? Reciprocal function. Secant. C goes to S. S goes to C. Sine and cosecant. Cosine and secant. So the derivative of tangent is secant squared. Is that obvious? No, but we did the work. And what are we doing? What do we keep doing? We learn rules, we learn derivatives, we use them to get higher, weirder functions figured out, right? We know sine and cosine from the limit definition. We know quotient rule. Together we know what the hell tangent is. What about more paper, Jeff? My kingdom for more paper. There we go. Okay. So not surprisingly, I'm going to ask you to please, if f is cosecant, no, let's do secant first. Figure out, don't say anything. Don't say anything. Figure out what the derivative of that is. Of course, how are you rewriting that? 1 over cosine. I like it. Let's see top first. What is the derivative of 1? Is that cool, everybody? That's definitely 0. 1 is a flat line. It's got 0 slope. This whole piece goes to nothing. What's the derivative of cosine? So negative sign is sine. Is that all right? So this piece goes to 0. That's negative sine times negative is positive sine over cosine squared. Can we simplify that a little bit? Yeah, so this will be like if I do a sine over 1 of the cosines times 1 over cosine, I get tangent times secant. And actually, I think of it the other way around. So the derivative of secant is secant tangent. I think of it the other way around, but that's all right. Holy shit. So I want you to, so here's, all right. What was the derivative of sine? Cosine. What was the derivative of cosine? Negative sine. All the co stuff has negatives. That's one reason we identified the co stuff with co. That's one of the many reasons. So for example, without doing all the work, I could totally do all the work, but the derivative of cosecant, let's see if you guys follow this, is negative cosecant cotangent. Do you see the analogy there? This is beautiful. Secant is secant tangent. Cosecant is negative cosecant cotangent. Analogous. And how do you prove this? The same way we prove that, we just put 1 over sine and then go to town. Okay. Maybe. And of course, the only thing we have left is cotangent. And recalling that the derivative of tangent, what was that? Secant squared. What would your guess be for cotangent? I think you almost got it. Almost. It's a co, so it's going to be negative. Why did I have trouble? Okay. That's really nice. That should make it a lot easier to memorize this as you need to, right? All the co stuff is negative with co stuff, right? It's kind of nice. Okay, I like it. Everybody's looking. We still have time. Too bad. I want to do one more thing. I'm not going to fully get into this yet. I'm not even going to tell you what I'm about to talk about. We're going to do one quick little thing and we'll finish it up next time. I know I just said the magic words, but we're not leaving yet. Especially if I can't find paper. Just give me some. I am not good at making sure I have enough paper. Anybody want brownie points? There we go. Oh, yeah, look, I did it. Yay. Okay. Now watch this, watch this. All right. Okay. If I have this function here, what do you got, Jeff? Okay. And if I had to take this guy's derivative, we would have to multiply this out. So because I don't currently know how to handle a function inside of a function. I don't know. But I want to show you why. So help me out. What do you get when you multiply this out?
9x squared plus 6x.
Okay. So what's the derivative?
6x.
Yeah, they're squared. Plus 6. Okay. Is that cool? Okay, I like it. And couldn't I, can't I kind of recover this? Again, this next step doesn't make any real sense, but I'm going to do it anyway. Isn't this true? Do you see how it's kind of nice that it's related to this somehow? Now, watch. If I erroneously, that's a word. If I erroneously believed that I could just do the derivative by bringing the 2 down, do I get the right answer? No. What is it missing? Let me not even do that. I'm missing a factor of what? I'm missing a factor of 3 to make it correct. What is the derivative of the inside? Freaking 3. Interesting. I love you guys. All right. I remember how people said, this is how I always teach this, but I remember people that know chain rule saying you hated it. I'm trying to build up some motivation as to why it has to exist. It is what lets me get the piece I would be missing if I treated it like it could work like the other stuff. It can't. This is proof that it doesn't work the same way. It's missing something. So what if, okay, last thing for today. Let's have one that's a little more interesting to look at. What if I had, nothing too crazy, Jeff? Sure, Jeff. X cubed minus 1 squared. That's just a little more interesting. So the right way, the wrong way, and let's see what it's missing. So if we do it the right way, and by the way, I really want to showcase this. Do you see how I didn't put a prime until I'm actually doing a derivative? The first step here was just simplification, yes? So don't just automatically put a prime. You're going to screw yourself over. All I'm doing in this first step is rewriting g of x. Is that cool? And what is this guy's derivative? I like it. And if I want to kind of do like we did before, wouldn't you pull out a 6x squared, right? And then we left with x cubed minus 1. Do you see how I kind of recovered this? That step is nothing we have to normally do. Actually, this would be if I need to find where it's horizontal, right? Factor it and get the zeros, yes, but anyway, it's not what we're doing. So what if I did this the wrong way? Let's see exactly what my answer is missing if I do this the wrong way. If I do this the wrong way, I just think, oh, it's something squared, the 2 comes down. What am I missing to make it correct? I'm missing a 3x squared. What's the derivative of the inside? Frickin' 3x squared. Holy shit, it seems. Is this enough proof to make a general rule? No. We have to actually go back to limit definition to make a rule. But this is definitely motivation to know that the freaking power rule doesn't work on this. If the inside is more complicated than x, I can't just take the 2 down and be done with it, right? If it was just x squared, it works. Because, for example, what's the derivative of x? 1. So then I would be missing a 1, so I'm not really missing anything. So if the inside is just x, I don't have to worry about this because then it would be times 1. But if the inside is anything more complicated, I can't just use the basic rule of the power coming down and going down by 1. I can't, because then I'm missing what seems to be exactly the derivative of the inside. So what's going to happen, what we're going to prove, is to do the derivative of a composition. You do the derivative of the outside function times the derivative of the inside. They each get a turn. That same theme, right? Each piece gets a turn. So we're going to prove that next time. And that is the actual next time, meaning it's over. So you guys can head out. Let me know if you have any questions for the moment. Where was this? This was section, yeah. 3.3 is trig and 3.4 is this. So we just sort of did a baby step into 3.4.
Oh, I thought it was 3-3, or just
3-3 is trig.
product and then.
3.3 is trig.
Oh,
Yeah. That's the stuff we just did. Yeah. All right.
Wait, you know how to get 63? I know we did it on the board.
Not one that's.
good,
See
yeah,
what I
yeah.
got here. I got ones that have writing all over them. Yeah, look at you. You can have that. This is the one where we worked it all out.
You said it'd be like.
Thank you. Sure.
Bro, do we have to do 63?
What do you mean? Well, remember what I said. I basically said you don't have to.
Okay.
I want you to try. I want you to write something down.
Okay.
But like I said, it's sort of like a bonus.
Okay.
Yeah,
I'm just looking at the board and it looks like French.
it is.
I mean, as long as you remember.
See you.
Did you get my 2.7?
Did I do one? Also?
Did you get my 2.7?
Probably.
I believe I did.
Yeah.
Yeah, okay. Oh,
Sure.
That was for
70? No.
Oh,
yeah.
So I turned this in.
Yes. And you do have until the day of the next test. But if you feel pretty confident about it, you can turn it in now. You do have time though if you want to. It's up to you. Oh, thank you. That'll be good for next
I
time.
have a literal entire sheet of printer paper at home.
Yeah, I keep forgetting to go to the print shop too. They have more scrap. They have all
Bringing
kinds of
some on
scrap
Friday.
paper.
I'll just hold on to it till Friday.
Yeah, yeah, good. It's all good.
Thank you.
So you said tutoring is in person now. What time are they in?
10 to 3 Monday through Thursday. So it's if you go in Canvas in the modules where I have the tutoring, it's updated to show that. And we still have the online also, and we still have the net tutor, and we still have the online appointments. Yeah.
Is that for the library?
Mass Study Center. Yeah, in the Mass Study Center. It's in the tech vault. Yeah.
Probably not hard.
Cool. Yeah, do it. Sure.
Go to us. Did you write that homework up there? Because it's thing or?
Yeah, because it didn't say every fifth one, so it made it look like you're supposed to do all of them. But I meant to say every fifth one, and I just forgot to put it on there.
Cool, thank you.
Sure.
Okay. So you're trying to plug a negative x into this one and
Yeah,
make
I
it
mean,
equal what it is.
I
with a
really
regular
want
x.
that to make sense. It's all about